name is Ashutosh Pitkar, and I'm a mechanical engineering student at Miami University. In the summer of 2020, I conducted a literature review on friction and wear behavior of PTFE and its composites. This basically means that I tried to look at some studies that have been done in the past that look at the wear and friction properties of PTFE, and I have tried to make a small compilation of all the research, and I'm trying to present it through this literature review. Now, I would like to thank Dr. Mark Sidebottom, who was my advisor for this research. Without further ado, I will now begin. Now, what is PTFE? It's a fluoropolymer, and it's a short form. It basically stands for polytetrafluoroethylene, a tongue twister, and which, because it's a tongue twister, it's called PTFE, which is much easier to say. Um, what are the applications of PTFE? It's widely used in sliding and dry lubrication applications, and the reason why it is used in such applications is because of its properties. It has a high melting temperature, a low friction coefficient, and it's chemically inert. The main concern with this polymer is that it has an undesirably high wear rate, on the magnitude of 10 to the negative 3, 10 to the negative 4 mm cube per nm. And this is not a good sign, because uh, if it has to be used for a long period of time, and if it has such a bad wear rate, then that would create a lot of volume and mass loss, and that's why we don't want such a high wear rate. We want to decrease its wear rate. Um, let's talk more about the chemical structure of PTFE, uh, and explain why it's a fluoropolymer. The reason why it is also called a fluoropolymer is because you have a carbon and a carbon atom bonded to each other, so covalent bonds. And similarly, this carbon atom, or each carbon atom, is also covalently bonded to uh, two fluorine atoms. And this is the chemical structure. This is the basic chemical structure. And this N basically signifies that this particular structure, as you can see here inside these parentheses, this keeps repeating for a long period of time, for a long amount of length. So this structure keeps repeating for a long time. And that's basically what a polymer is. It's a very long chain. And you have a carbon. And why is it a fluoropolymer? Because the only other um, element in this structure is fluorine. So it's a long chain containing carbon and fluorine and no other element. So fluoropolymer. Contact schematic. As you can see here, this is the most basic view of your apparatus. You have your load cell, which is used to change the normal load applied. Um, this is your composite pin, which is basically either it can be PTFE by itself, or it can be a PTFE composite. And this is your counterface, which is generally stainless steel. So when I'm saying which is generally stainless steel, I mean that in the research that I have done, most of the research groups have used a counterface which was made out of stainless steel, but varying degrees, varying grades of stainless steel, meaning that they were differently heat treated. Um, Now, so this is your apparatus, and what is the measurement and observation? So in most of the research that that I will be talking about, it has looked at the wear rates, it has looked at the friction coefficients, it has looked at the surface morphology, meaning how has the surface. So basically, they observed the counterface surface before, after, and at several intervals during the experiment, and saw how the surface, saw the evolution in the surface, to look for any cracks, to look for any scratches, because that would also tell us the some factors that may influence the wear rates and friction coefficients. And finally, we'll also look at the mechanism that is actually causing these changes in the wear rates. This formula you can see, which is K represents the wear rate, is equal to mass lost divided by density times the force times distance. Now this formula will be used in all the research that I've conducted, because um, this formula is how the wear rate is determined. Mass lost can be, so the way the mass lost is found or calculated is through through taking breaks in the experiment. So you start your experiment, you take a break after a certain number of distance traveled or a certain number of cycles, and then you calculate the initial mass of the composite pen, and then you calculate the final mass. That will tell you the change in mass, which is basically the mass lost. Density is the material property, which is assumed to be constant. Normal force is the force from the load cell, and the distance traveled is what your computer will calculate for you. So you can find these values fairly um, simply, and that's how you can get the wear rate. Now these two, this image and this image, is almost, you can see there's a huge difference, but this image is kind of a magnification of this particular part of the entire apparatus. Your load cell, your composite pin, your composite pin and your counterface sample. And this is your entire other setup, which is also involved, but we will not be dealing with that setup in the experiments. Now this is your computer data acquisition. Like I said, uh, parameters like distance traveled can be calculated through the computer. The computer will do that work for you. Now these are all the parameters, or I should say variables, that I studied in my research. There are a lot more variables that exist, and probably there are a lot more that have still not yet been found by people. But there are these variables that I have researched, um, and I have divided my work into three PowerPoints for these three topics. So in each PowerPoint, I'll be covering each topic. So one PowerPoint will deal with filler content and geometry. Next one will deal with internal and external variations of sliding interface, and the other one will deal with tribochemistry and tribosurface. So as you can see, there are a lot of topics and a lot of research that is being done. Um, and it's a very complicated field, a very complicated mechanism, a set of very complicated mechanisms that are complementing each other, that are going on at the tribophase, which are determining the wear rates, as you will see when I present you the work. So thank you for listening, and I hope that you will look at the other PowerPoints. Um, and I would also like to acknowledge the Miami University Library Resources and Google Scholar, because the articles that I found were either available on this or either available on this resource or on Google Scholar. And I would also like to thank Kaltura recording tool, because that is what I use to record this video and the videos that I'll be recording for the other PowerPoints. Thank you.